Hey there, nerds. Sorry I couldn't be here with you today. I'm out with the 10th grade ski trip, so I'll have to say hi from afar, and you'll have to do a little math magic on your own. You just flip it behind your hand like that, and then just pull it out like that. But from the front, looks like that. All right, so we are on 5.7 dependent compound probability, and that sounds fancy because it kind of is, because the probability depends on what you've done in the past. So let's get started. Let's try it out. In the top of your notes, you can go 5.7 dependent compound probability, and try this warm-up. You got two identical bags of marbles. Why marbles? It's easy to visualize. It's easy to see. So we want to find the probability that you pull a red and then a blue. Like pull a red out of this one and then pull a blue out of that one, right? You could think about this as the same as pulling one and then putting it back, or just pulling different ones out of different bags. So the probability shouldn't vary. All right, so try that. Pause me and try that. Go. Okay, here we go. So we figured out that there's, 7 in here, and 5 of them are red. So the probability of pulling a red one out of this is 5 out of 7. And we want to do that, and then also pull a blue out of here, so that's 2 out of 7. So we're going to have 5/7 times 2/7. You multiply the top, multiply the bottom, you get 10/49. Turn that into a probability 22-ish% for pulling marbles. You may have not lost all your marbles, but there's definitely a hole in the bag. Not sure what that means. We'll have to do some homework questions later. Answers are up on the VLE, and so let's get to it. We saw independent events last time, and that's when, just like the warm-up, the one event doesn't change the other. You roll a die, you have the same probability of getting a 2 on the first, second, third, fourth rolls. It's all the same, right? So we throw some fruit in a bag, lemons and limes, and if we had like 2 lemons and 1 lime, we throw them in a bag, and we're fishing around trying to pull one out because we need to fend off scurvy. We have a 2/3 probability of pulling a lemon and 1/3 of pulling a lime because there's 2 lemons and 1 lime, right? So if you were going to make a compound event out of that, it'd be like pulling a lemon and a lime, or a lime and a lemon. So in this case, we want to find the probability of 2 lemons with replacement, right? So pull a lemon out. On the first pull, you have 2/3 chance of getting a lemon and 1/3 chance of getting a lime. And so if we want 2 lemons, we're going to have to follow this branch and say, yes, okay, first I got a lemon. You say, hey, great, I got a lemon. And then you put it back in the bag. That's what with replacement means. You put it back in, and then you're on to another event, right? And so you have, since you've replaced it, you haven't changed anything. You still have 2/3 of getting a lemon and 1/3 of getting a lime, right? So if you want 2 sets of lemons, quiet down, other computer. 2 lemons, you go 2/3 times 2/3, right? 2/3 times 2/3. It's the exact same thing as this, right? 5/7 times 2/7, right? 1/3 or 2/3 times 2/3. Great. Independent events one doesn't depend on the other, right? Ain't nobody got lime for that. So we're going to dependent events because sometimes one thing affects the other. Let's stick with the fruit, right? Oh, my fruit is back behind my head. That's no good. I was wondering why I had a headache. Dependent events, one event does depend on the other. The probability, one does depend on the other. So we still have 2 lemons and 1 lime. We throw them all in the bag, and if we pull, like the first pull, if we pull out a lemon and we eat it, here I'll symbolically tuck this behind my head, in my neck. If we've eaten this, now there's only 2 options in the bag because our first event has changed the probability of the next one. All right, so our second piece of the tree diagram will change. So let's just, for argument's sake, say we pulled a lemon. We took this route and we had 2/3 of probability of pulling a lemon. Great, we got a lemon. So now what's left in the bag? Well, a lemon and a lime, and that should be reflected here in this piece of the diagram. See, now we only have, let's get rid of that, we only have 1, 2, we have 2 of these, and so now we have a 50-50 chance. We have 1 out of 2 is a lemon, this, and 1 out of 2 is a lime, that, right? So, so that's this branch. And so you could say, hey, what's the probability of pulling 2 lemons, right? And the probability would be 2/3 times 1/2, right? So that would be 2/3 times 1/2, and so 1/3 of the time, right? Because the 2's cancel. So the other branch down here is like, what if we pulled the lime? Well, if we pulled the lime, 1/3 of the time we'll pull a lime because there's 1 out of 3 of those fruits are limes. And then left in the bag is only lemons. So the other branch would look like this. I have a 100% chance of getting a lemon because that's all the fruit that's left in the bag, and 0% chance of getting a lime. Okay, so let's run a little probability with that. This notation we'll talk about a little bit more. You can write that down, but it's not one of our focuses right now in this lesson. But you're just going to be using these tree diagrams just like independent compound probability, except these change a little bit. But you do the same thing. You want to figure out the probability of getting a lime and then a lemon. You go 1/3 times 1. Yeah. So let's look at something real quick before we go on. This probability with getting 2 lemons is 2/3 times 1/2. So this turns, if you multiply 2/3 times 1/2, you end up with 1/3, right? Same thing here, 2/3 times 1/2. This is 1/3, and this is 1/3 times 1, so that's 1/3, and 1/3 times 0 is 0. If you add those all up, you should get 1. You always should get 1 if you're messing with these tree diagrams or probability, because something has to happen. So 1/3 plus 1/3 plus 1/3 is 3/3 is 100%. 100% of the time, one of these things should happen if you're pulling twice, right? So one way to check that your probability is good is just add up all of the probabilities. All right, let's try the same thing out with marbles in a box, right? It's easy to visualize. It's pretty straightforward. So you got 2 blues, 3 reds, and a yellow, and we want to try to find the probability if we get a blue and then a red, right? Well, it depends on if you put it back or not. So let's look at it pulling a blue and then a red with replacement, right? We're putting it back. It's independent. So pull a blue. You've got 2 out of 1, 2, 3, 4, 5, 6. So 2 out of 6 are blues. So that's this line right here, right? 2 out of 6 are blues, 3 out of 6 are reds, 1, 2, 3, and 1 out of 6 are yellows. Great. You look at it, and right now you have 2/6 chance of getting a blue. You go, great, I got a blue, and you put it back because you replaced it, right? And so now your new probability looks like this. Let's cover this up so it doesn't freak you out right now. So when we put it back, you'll notice that the reds, still 3 reds, right? 3 out of 6, 3 out of 6. Still 2 blues, 2 out of 6, 2 out of 6. Still 1 yellow, 1 out of 6, 1 out of 6. And if you look at all the other branches, they're the same. 3, 6, 2, 6, 1, 6, 3, 6, 2, 6, 1, 6. And 3, 6, 2, 6, 1, 6. 3, 6, 2, 6, 1, 6. We haven't changed anything. This looks like this, looks like this, looks like this. And so you can just follow this through and say, hey, probability of blue is 2/6, and then red is same as what we started, 3/6, and you just multiply them together, right? You should get 1/6 if you multiply them. Great. Now, if you don't replace them, it looks more like this. Let's cover this up so you don't freak out. We have the same initial start conditions, right? 3, 6, 2, 6, 1, 6. Let me cover these up too. This is a lot easier to do in real life. Great. So here's pulling a blue. You still have the same initial start conditions. I have 2 of those out of the 6 are blue. So that's this piece, right? But without replacement, if we pull it out and then like throw it away or give it to a friend or whatever, now we're sitting with a different number total in here, 1, 2, 3, 4, 5. So you'll notice that all of these have blah over 5, something over 5, because there's only 5 left because we've thrown one away. So now the probability of the red afterwards is 3 out of 5, because 1, 2, 3. And so the probability of pulling blue, then red, without replacement is 2/6 times 3/5. Right? Multiply those together, multiply the top, multiply the bottom, simplify, and you go from there. Great. Also, so things change around here, right? Depending on if you pull red, blue, or yellow, and we'll look at that in a second. All right, so let's try some problems with that. Here are all the diagrams. Ka-ching. And I want to look at what's the probability of pulling 2 yellows, right? So with replacement, that's this guy, if you put it back, there's a possibility of getting 2 yellows. You have 1 in 6 chance because there's 1 out of 6, and then you look at it and say, hey, great, I got a yellow. You put it back, and you have another 1 in 6 chance. So it's 1/6 times 1/6 is your probability, 1 in 36. Without replacement, there's only one of them. So if you pull out the yellow and look at it and say, oh, that's a black dot. Say, hey, I got a yellow. Great. That you had a 1 in 6 chance of doing that. But if you don't replace it, you throw it away, you eat it, you feed it to your dog, there's no more yellow in here. So 0 out of 5 of those are yellow. So this is 1/6 times 0, right? So 1/6 times 0 out of 6 is going to be 0, right? That doesn't happen. All right. So let's look at this. Let's look at the same color, right? I want the probability that we get the same color, and this is a little bit tricky because we have to follow a couple of different branches and then add them up. So this is like a little bit tougher, but you can follow me along. So let's just look at with replacement first. So if we are pulling out a color, looking at it, and putting it back in, to get 2 of the same color, we can either get red, red, right? None of these other ones in this arm would work. We could get blue, blue, or we could get yellow, yellow, right? Those are the same colors. So to get red, red, you'd get 3/6 times 3/6, yeah? So 3/6 times 3/6. Let's do this. Put it over here. 3/6 times 3/6. So that's with replacement. That would work. And the blues, I think that's 2/6 times 2/6. 2/6 times 2/6. And yellow, yellow, 1/6 times 1/6. Oh, can't see that. Times 1/6. Oh. Great. So you'd multiply and then add them up because all 3 of those probabilities would work for you. Without replacement, you do the exact same thing, but your second value changes. You get 3/6 times 2/5 because this changes. Within the blues, you get 2/6 times 1/5, right? And in the yellows, you get 0. Cool? So that's just a little intro. Give it a shot in your homework. It's just 3 problems. I know there's sub-problems. Build the table, right? Build the tree diagram. It'll help. Don't just do it in your head. Build the tree diagram, right? Because it's really easy. Just make it look like that, right? 2/3, 1/2, and then you can just multiply things and use this to help you problem solve. Once you're good at it, then do it in your head. It's out of the text, it's on the VLE, and here are the upside down solutions. So you have to flip the whole thing upside down like that. Wow, neat. Okay, go.